Because remember, the form of that t-distribution, how flat it is, depends on the size of the sample. And that's where this degrees of freedom comes into play. In addition to that, a little bit of a wrinkle. The multipliers that we had for our previous situation, there were only 4 values that we worked with, right? So we could easily write those 4 values into our notes, and it was something like 1.645, 1.96, 2.38, I think something like that. I don't remember the exact numbers. But those are the 4 values for the various confidence levels for the z-distribution. But now what I've got is the distribution depends on the size of the sample. So just like table A.3 changing, now what we've got is instead of just 4 values, we've got an entire table. Table A.2, and there's actually a copy of that table just inside your back cover of your text. So the inside back cover, the 2 pages there is the z-distribution. Page 1 back, where it says t-star multipliers for confidence intervals, that's table A.2. And that table looks something like degrees of freedom. And it has a 0.80, 0.90, 0.95, etc. Okay? What you do is you determine what your confidence level is that you want. That determines the column that you're looking in. So a 95% confidence would be the 0.95 column of this table. And you determine degrees of freedom. Across the top here it has something like 3.08, 6.31, 12.71, and then up. Okay. So remember that a 95% confidence interval for a z-distribution, for looking at proportions, was 1.96, correct? That was the multiplier. What we have now is, if I have a sample of size 2, that would be degrees of freedom equal to 1. So look at row 1, for a 95% confidence interval, the multiplier is 12.71. That means you're going to take the mean plus or minus nearly 13 standard errors in either side of it. Does that sound particularly useful? It's probably not of much use at all. And that's essentially what it's telling you. If you look at that column, that 95% column, you'll see that those numbers drop fairly fast. And we get down to samples of size 9, so degrees of freedom 8. We're down to 2.31. But it takes up until samples of size 60, actually 61. So samples of size 61 would give me degrees of freedom of 60. That gets to the point where I have a multiplier which is just 2. I'm still not down to 1.96 though, am I? 1.96, I actually have to go down to infinity. So if you look at the bottom row of that table, that is a degrees of freedom equal to infinity. That says that my t-distribution now is identically the same as my z-distribution, and in fact those numbers across the bottom of this table are identically the z-star multipliers we had for the z-distribution. So this is going to be a z-star. My standard error, similar to what we've done in other situations here, it's going to be the standard deviation, and I'm going to replace the sigma with the best guess I have, which is s. So this is s over square root of n. So we then have s over n here, and we have our formula for our confidence interval. Conditions. In order to do inference, I need to have some confidence that the conditions are met for my confidence level to be accurate, for my p-values to be accurate, and so forth. So I need to have some confidence that the underlying distribution for x bar, or the sampling distribution for x bar, is close enough to my theoretical distribution. Okay, in this case, is it close enough to a true t distribution? We had three conditions. The first one was what? It's the same as what it has been all along. So the first condition is...
N is greater than or equal to 10?
Nope, that's the third condition. That's usually the size. We'll get to that in a second. Usually the first condition is that there actually is something in the population that we can measure, that there's a true population that we can measure the value for, or that there is a true experimental condition that can be repeated that will allow us to measure something. Okay? So in this case, you could say mu exists, or there's a true population, or a random process that we can work on. Condition 2, the second condition is that we have a representative sample, right? Our sample has to be representative of that underlying population. So either a representative sample or a representative set of measurements from an experiment, but a representative set of data for the target population. Okay? Now those are identically the same as what we had for previous cases. The third condition is similar in that we need to have a large enough sample. But it's a little different than what we had for single proportions or two proportions. Okay? We're not going to work with the n times p. First of all, we don't have a p in this anymore. The population parameter p doesn't exist here. So what we need is we need conditions under which this is valid. There's actually two conditions that we can satisfy. It can be either of these two conditions. The first one is the population to begin with is bell-shaped. So if we are sampling from a bell-shaped distribution, so something that is clearly normally distributed to start with, then it doesn't matter what the sample size is. The sample size can be 2, and we can trust our statistics. However, if we have a multiplier of 12.71 on a sample size of 2, we can trust it, but it ain't going to be worth a whole lot. So we need to have some sample size here. The second possible condition, if we can't say that the underlying population is normally distributed, okay, and quite often we can't, then what we need is n greater than 30. Okay? And if the sample size is greater than 30, then we should have enough of what we called central limit theorem effects kicking in, from what we talked about back when we were talking about sampling distributions, that we're going to get approximately a normal distribution. And if you think back to our rectangularity experiment, that's exactly what that was demonstrating. We started out with something that was very definitely not normally distributed. We sampled from that. We found that samples of size 5 didn't act well at all in terms of shape. But by the time we got to samples of size 25, the shape was beginning to look roughly bell-shaped. Okay? And we get to samples that are larger, we get a better bell shape out of it than that yet. To get a nice clean bell shape, you usually have to have samples of 200 or 300 to get a nice clean bell shape. But they're usually good enough by the time you get to a sample of size 30 that we can trust our results. Okay? So either of these conditions would be satisfied. Okay. Start working on problems 11, 21 through 24. What we'll do is, in about 5 to 10 minutes, we'll come back, we'll take a look at 21, probably talk through 22, so try to get at least 21 and 22 finished. We'll come back, we'll talk our way through those, work through those two problems, then I'll give you some more time to work on 24, and then we'll come back and talk about 24.